right, I think that's a sign to start the session of today. So good afternoon, everybody. Welcome to the last session of this of today of this workshop, of this second day of the workshop. This is the session on machine learning in wavefront sensing. We have 5 very interesting talks today, including one invited talk. And we're going to start with Jean-Pierre Véran. Welcome, Jean-Pierre, who's going to present about mitigating the pyramid wavefront sensor non-linearities with artificial intelligence. So, Jean-Pierre, you have 12 minutes for your talk, plus 3 minutes for questions. And I'm gonna let you know when you have 1 more minute. Okay, thank you.
All right, thank you. So before I start, I would like to say that I'm certainly not an expert in artificial intelligence and machine learning, but my colleagues here who are associated with the Canadian Astronomical Data Center, certainly they are, and they routinely use these tools to do data mining. So, basically I merely bring them the problem and they are the one who try to solve it. So I think by now, we have discussed quite a bit about pyramid wavefront sensor being non-linear. And basically what it means is that if we use a linear reconstructor like an MVM, then we are getting reconstruction error. And we can always increase the modulation to reduce non-linearity, but then we are losing in sensitivity. And so just to give a motivation for this work, in the case of nefarious in NGS mode, so we use a pyramid wavefront sensor with a 3 lambda over D modulation. Well, in our error budget, the total wavefront error is 156 nanometer RMS. And as part of this wavefront error, the wavefront sensor non-linearity accounts for 64 nanometer RMS. So it's not negligible. And so, if we want to do something and try to reduce this, we can either derive a nonlinear reconstructor, which usually has to be iterative, and that's related to the talk by Victoria yesterday. Or an alternative approach that I'm going to present today is to use machine learning to learn about the nonlinearity and implement a machine learning-based nonlinear reconstructor in the form of a neural network, for example. So all the work that we have done so far is based on simulation. So what I do is that I generate wavefront maps, and mathematically I can compute the model coefficients that are in this wavefront map. Now, at the same time, I can compute the measurement from a pyramid wavefront sensor, and then I can compute the slopes, and then I can apply a linear reconstructor, and then I can compute reconstructed coefficient based on that. And to do this, I use the Archetree Passata pyramid wavefront sensor package. So, the alternative is to use a different reconstructor based on machine learning. And so, the goal is that, the coefficient that are provided by the reconstructor are as close as possible as the true coefficients. So just to give more detail, in this simulation, I use a pyramid wavefront sensor model that is that represent what's going to be implemented in GPI2. It has 60 pixels in the pupil diameter, 3 lambdas over D modulation. And the wavefront map that I'm generating, I'm trying to make them resemble what's typical for a residual wavefront error. So after error correction, and so I generate them with a f-2 PSD, and I generate them with an amplitude that's between 0 and 200 nanometer to account for the fact that, well, sometimes the turbulence is strong and you get strong residual, and sometimes it's not so strong and you can get very, very low residual. It changes with time. So, as a non-expert in machine learning, this is what I understand on how a neural network works. So here I show a basic 1-layer neural network you have one layer of neurons. There are 512 of them in this case, and they basically convert the pixel values into model coefficients. So here we can say that the neuron layer is dense because each neuron is connected to all the pixels are input. But what the neuron do? It's a linear operation. It's pretty much an MVM. It's just a linear combination of each neuron is producing a linear combination of its input. So in order to implement a non-linearity in this process, we need what's called an activation layer. And in this case, it implements a non-linear operator, which is called the ReLU. It's defined here, and yeah, basically that's how it works. Now, you know, usually to be efficient, neural network they need several layers, and here you can see that this can create quite a bit of parameters. Like the number of parameters can increase quite a bit. So this is where the convolutional neural network come handy, because in that case some of these layers they are implemented simply as convolutions, and so they have relatively small kernels, so the number of parameters is reduced. So anyway, I wanted just to show you sample results. So initially, in the case where there is no noise on the wavefront sensor, and here all these results they are created, basically. So I created, one data set of 20,000 independent wavefront maps. So always the f-2 PSD and amplitude between 0 and 200 nanometer RMS. And then the neural network is trained on 18,900 and then is tested on the remaining 1,100 sample. And so here we see that, so here in this graph, we examine the RMS wavefront error as a function of the mode number. And we compare in dashed lines the linear reconstructor with two instances of the machine learning reconstructor. And we see that, yes, the machine learning reconstructor does better, produce less residual RMS wavefront error. And we see also that the convolutional network, which is in orange, produce lower residual. So in that case, we reduce the total RMS, which is the integrated over, like here we are reconstructed 100 modes. We reduce the total RMS by something like 40%, 40 to 50%. So this is quite nice. It's also interesting to see how these reconstructors do as a function of the amplitude of the phase screen. Like I said, we generate amplitude between 0 to the left and 200 to the right. And so here it's quite interesting because we see that for low amplitude, the linear reconstructor does better, of course, because the wavefront sensor is linear for this amplitude. But for high amplitude, the non-linear reconstructor does better. And where it's interesting is to see, the mode number where, you have this crossover where the linear reconstructor starts doing worse. And this is, in that case, we look at the tilt mode, but, other modes, they have a similar behavior. Now we are trying to look at the robustness of the reconstructor, because like I said, when we train, we generate some wavefront maps with some statistical content. And so what happens if the statistical content is different when we use a reconstructor? And this is an example where we test on a set that has a 2.2 f-2.2 power law, but we train with either an f2.2 power law or an f1.8 power law. And then we see that, not surprisingly, if we train with the right statistic, we do better here in the case of the purple. But, we don't do much worse if we train on a different statistics. It works also if we have noise. So in this case, this is a magnitude 10 simulation where we have about 11 counts per frame and subaperture and we have photon noise. And we see that we get still a significant reduction in RMS wavefront error. Instead of estimating only 100 mode, we try to estimate more than that, but we see that after some number of modes, really as a machine learning reconstructor doesn't work very well. And it might be because these modes are just too noisy, or it might be because we need to use longer training session. We'll investigate this. We've start looking at the computational complexity. So here the reference is the MVM, the linear reconstructor. Here it's estimated in this case at 2 megaflop. As we complexify our machine learning architecture, we need quite a bit more operation, up to 10 times, up to 100 times as many operation. However, these operations can be executed in parallel, a lot of them, and this is an example of benchmarking using the Colab GPU resources. And in gray, this is a histogram of the linear reconstructor, and you see that's a machine learning reconstructor. They don't require that much more time to execute. And so now there's been no attempt to try to implement this in real time or anything, but that's sort of give a ballpark. So, already at the end of the talk here, so in conclusion, I think we are finding some very promising preliminary results that show that, indeed a CNN can be efficient at implementing a nonlinear reconstructor, and that we can reduce significantly the nonlinearity errors, especially on the lower order modes, actually. Yesterday on Discord, Sebastian pointed to me a paper that he wrote with a colleague in 2020, where he looked also at CNN for pyramid wavefront sensor reconstructor. And what he found was interesting, because he found that the CNN was efficient as long as it was complementing the MVM, and actually that's something we haven't tried as a dual approach, where you actually you could use the MVM to do the heavy lifting, get out what's linear, and then the CNN as a complement. But we do find that just the CNN seems to work, so there might be some potential to improve with this dual approach. The computational burden appears to be manageable, to be confirmed. So as a next step, we are planning to further develop our simulation, and also we would like to try to test this in the lab and also on Sky on our Revolt demonstrator. So that will be a talk tomorrow by Tarun, who is going to explain what Revolt is. It's a demonstrator that can go on our local 1.2 meter telescope. As a more perspective, we think that we could, in fact, this is a sort of a spatial reconstructor which could be coupled with the temporal aspect of trying to predict the turbulence. I just want to mention that we did some recent work where we reprocessed some altered telemetry data to see if prediction could have improved this acquisition. And in fact, we found that the machine learning reconstructor, machine learning predictor works, but actually we found that in this data it doesn't work any better than the sort of data-driven linear predictor that Mike talked about yesterday. So that also has to be confirmed. But for now, we see the most promising aspects of using machine learning is in the reconstruction and overcoming the non-linearity in the reconstruction, and perhaps over imperfection in the system more than actually doing prediction. So anyway, that's all what I wanted to say. Happy to take questions.
Thank you very much, Jean-Pierre. I think we have a couple of questions and just a couple of minutes just to answer them. One of them is from Andreas Oberede. He's asking whether could you mix the reconstructors, AI for the lower order modes plus classic linear for the high frequencies, lower OG anyways?
Yes, that's exactly what I'm thinking, and this is why we used we try to focus on the first 100 modes, and with this graph you see that high order mode it doesn't work. So that's exactly what I would do. I would have an MVM that reconstruct modes 101 to VN, and then the machine learning reconstructor for the low order mode. Yeah.
Okay, great, thank you. And another question from Benjamin Gerard. Interesting that the ML reconstructor does worse for higher order modes. What spatial frequency does this point where performance is worse than a MVM correspond to? Any further thoughts as to why this might be the case?
Yeah, so that's, I mean, here it's in order of mode index. So I don't know exactly what's the spatial frequency, but it's pretty low. So I think like I say here, it's probably we might need some more training sample, like maybe training on 20,000 sample is not enough. And actually we've tried to we started to look at using more sets for training. I think it seems to improve a bit, but not significantly. And I think also these modes they are very noisy. So at some point, like if you try to there's no way if it's just random noise, there is no reconstructor that will do that will do better. So I think it might be the case that the SNR is just too small on these modes.
All right, thank you very much, Jean-Pierre, for your presentation. I think there are other questions, but we would like to encourage the audience to use also the Discord channel for further discussions. Right, so we would like to continue with the program. Thank you very much. Again, we continue with Camilo Weinberger, who will present about the neural network applied to predict optical gain in AO systems. So Camilo, you can, you are there, you can share your presentation and already start.
All right, thank you very much. Do you hear me?
Yes. All good.
All right. So I will talk about the neural network applied to predict the optical gains in a AO system. So first of all, I will talk about the motivation. I'm using a pyramidal system. The pyramidal system corresponds to an apex located in the focal plane of the beam, and is produced in this case produced for subpupils, but this system has not linearity, because if we modify the wavefront, we obtain that the focal plane is moved, and it lost a lot of information of the pyramidal system. For example, if you can see here in this experimental setup from loops, we can see there are two well illuminated subpupils, but there's not a lot of information in the other two subpupils. So in this case, if we want to have a better reconstruction of the system, we have to modulate using a modulation. It's moving the the focal plane around the apex of the pyramid. So we have more information, and we obtain a good measure of the pyramid. But in this case, if we have a better linearity, but we decrease the sensibility in the system. So if we are using a very big modulation, we lost a lot of sensibility, but we will have a more linearity in the pyramidal system. So how can we solve this problem of the linearity and the sensibility in the system? We can use a pyramidal system using a low modulation, like 3 and 5 lambda over d, and we can use a neural network to work well with non-linearity. In this case, we have two goals. The first one is a neural network working as a reconstructor. We train a neural network to predict the first 54 SCEx or Kelley molds, and in the second step, we test the neural network where the output of our system will be an optical gain for the pyramid prediction, because if we modify the optical gain in the pyramid, we can get a nice sensibility and a bigger linearity range. So our methodology is training and testing a neural network under our simulated condition. The condition is given by the condition of the specification of the OHP telescope, and I will talk a little more about that in the next slide. And also we generate a random aberration for strong and weak turbulent condition, because we want to make a kind of reconstruction matrix with not just with a low deformation as the pyramid system do. We want to include a lot of deformation to have a better reconstruction matrix. And well, why we are using neural network? Well, because if you can see here, we have different kind of air knots, and for the lower air knots, we have a more rugged surface, intensity surface. So if we include a convolutional layer in different with different kernel, we can get different results of the same image. For example, here, if we are using a convolutional filter of 1 cross 12 kernel size, we can get the horizontal convolutional values of the image, and in this case, the vertical values. And for bigger air knots, we have more softer surface intensity. So, for example, here you can see that in this case we have a softer value. So we can predict that that we don't need a more information in the optical gain, for example. Another example here, if we consider this simulation, if we have the simulation of the telescope that are we using for, if we include a air knot of 1 centimeter, has a 1.7 pixel of coherence, and if we include a bigger one, for example this one, we have a 9 pixel of coherence in the image and in each subpupil, for example. Well, about the simulation, we simulate the system using OMAO. It's an algorithm from MATLAB, and for all the simulation, we consider our atmosphere where the air knot is a normal distribution between 0.5 to 7 centimeters, the telescope, the diameter 1.5 meter, the OHP telescope, and the pyramidal has a modulation of 4 lambda over d. We consider these values because we want to, after this test, we want to test the system in a real condition with strong turbulence. And this is a little explanation of the pixel of each image. And for the training, we have an input of 2,100 image subsampled to a low resolution because we have some computing limitation, but it's not a big deal. And for the output, we have a training to 54 SCExAO kernel modes, and in the second training for the global gain, we are using one value of the output, get it from this equation. This is the relation between the SCEx mode of the ground truth in the simulation and the SCEx mode read by the pyramidal system. So this is how we are getting the global gain for the whole system. And for the results, we have the pyramidal error was calculated directly over the full size image. For example, the reconstruction of the pyramidal system here is using the full size image of a very high resolution image. And the network prediction was get from the trained image. For example, the lower resolution image, it was a part of the 1/4 the size of the real the simulation. And finally, the neural network reconstruction in the low values generate lower residuals than the pyramidal system. For example, if you can see here the residual error, and in the logarithmic values of the R0, we have that for low values of R0, strong turbulence, we have a residual pyramid. This is the residual for the reconstruction minus the ground truth given by this equation. We get that the pyramidal error was near to 300 nanometers, but in the case the neural network, we get that the error was in this case here in the gain and in the optical gain, we have that error is the half of the maximum value of the pyramidal error. So that's a very good news for us because we are considered that the neural network was trained with a low resolution image, and the pyramidal reconstruction was using a high resolution image. And this is zoom the image in the left part. In the left image, we have all the parts where the neural network was better than the pyramidal reconstruction. This is for 2.5 centimeter of R0. And for the high values, we have a better reconstruction in the pyramidal system because we are under the linearity of the considering the modulation. But it's a very good reconstruction because we have to consider that in this value we have a good sync in the sky, so it's not a big deal. The more important things is that for us under strong turbulence we have a better result than the pyramid.
1 more minute, Camilo.
Huh?
1 more minute.
All right. And finally, for the conclusion, we have the neural network won the pyramid linearity over using the same modulation in the system. So we have a better reconstruction and not more sensibility, but more linearity when we have a very strong deformation in the system. And in the case of the gain neural network, we can fix the problem of the gain using a low modulation. And also we have to consider that the optical gain are included in real time per each prediction. And also the most important, we can improve those results because we are using a low resolution image. So the next step is using a higher resolution to get I think a much more accuracy in the prediction using the neural network. And for the forthcoming work now in progress, we will compare these results in the optical bench loops here in LAM using a phase map and pyramidal system simulated in the SLM. And after that, we will close the loop and take a look about the stealth radio. And after that, the idea is test in Papyrus bench and finally in the observatory in OHP. I will talk a little bit the optical bench and loops. We will have here the start and the propagation, the start in the turbulence by the first SLM. And we will use, in this case, this SLM modulating the pyramidal system. And finally, we will get the first result. And well, thanks very much for your attention.
Thank you, Camilo, for your talk. Wonderful, it was wonderful. And now we have some time for any question from the audience. If you have any question, please, you can type it in the Q&A box. You can find a link in the lower part of your window, the Zoom window. So far, there are no questions. No questions, but okay, we see that there's some discussion already going on in the Discord channel. So maybe I invite you, I invite everybody to also use the Discord channel for their questions. So thank you very much, Camilo, for your wonderful talk. And now we're going to continue with the program. We have Maxime Kesnel. Maxime, are you there?
Can you hear me?
Maxime, we can't hear you.
You cannot hear me now?
I can hear you, but not much. Can you maybe increase a little bit the volume of your mic? I can see you very well, huh?
Okay.
It's all good.
So it's really not loud enough.
Yeah, the volume is a little bit low. Maybe.
Right now it's better or not?
It's a little bit better, but okay.
You think it would be okay?
I think it should be okay. We can just
maybe
make or loudspeakers a bit louder. It's fine. So maybe you can, if you like, you can share your slides.
Yes. Sorry, just. Sorry, I just have some issues.
Sorry, I don't hear you very well.
Yes, sorry. The fact that I had to change the laptop because I have some issues with my mic, but I cannot see my. Okay, I will. My screen is shared. Can you see the slide now?
Yes, perfect.
Okay.
Perfect. Now we can see you the slide in full screen, and we can hear you very well, actually.
Okay, perfect.
So thank you, and you have 12 minutes. for your presentation, and then some time for
Okay,
questions.
I will
Please,
try to be
go ahead.
fast. Okay,
Good.
so
No problem. Yeah.
so hello everybody. So I'm Maxime Canel, and I'm a third-year PhD student at the University of Liège in Belgium. And I would like to present to you some method we have been working on. So for focal plane reference sensing using a deep learning approach. And in particular, I will present some experiments and results I got with the vortex chronograph. And at the end, quickly, I will also talk about some application with experimental data we have been doing thanks to some data provided by the SCExAO team at Subaru telescope. So first, I would just like to give some context about what I am doing. So we work for exoplanet imaging, and we have too many limitations, which are very small angular separation and very high contrast between planets and the parent stars. And usually we use adaptive optics to reach higher resolutions, and also coronagraphy to suppress the starlight and reach higher contrast. But nonetheless, we still get some what we call quasi-static speckles in the focal plane. And the issue with these speckles is that they can be quite bright and they can look like planets as well. So of course, we would like to suppress them to be able to better distinguish planets. And for this, we would like first to understand where does these speckles come from. So the main origin of those speckles are considered to be non-common path aberrations, which are basically aberrations that occur in the instruments, but cannot be corrected by the wavefront sensor. So for example, any aberration between the beam splitter and the camera, but also between the beam splitter and the wavefront sensor won't be corrected, and so can produce speckles in the focal plane. And so focal plane reference sensing basically is to take our science image or point spread function and to try to infer the pupil plane phase aberrations with some method I will discuss. And then if you get this phase, we want to apply the opposite phase using the differential mirror to be able to cancel the aberration out and to get a cleaner PSF closer to the diffraction limit. So this is focal plane reference sensing, very basic words. There are a quite strong limitation for focal plane reference sensing, which is a phase sign ambiguity. So if you decompose your phase into the unequal components or the unequal polynomials, and if you look at the all of the polynomials that have an even radial order, such as defocus, astigmatism, or spherical aberration, the issue with this kind of polynomials or this kind of mode is that if you have the opposite mode, you will get exactly the same PSF. So I can represent this or just illustrate this with one example. So here you have one phase map and another one where I just switched all of the even mode coefficients. And in this case, you would get exactly the same in focus PSF. That's the ambiguity. But for example, some methods used to leave this ambiguity are using phase diversity, like including a defocus PSF. And so if you include a non-defocus, you will be able to leave the sign ambiguity because the response will be different in this case. But the issue with this kind of approach is that you will need to dedicate some observation time to get this defocus PSF, and this time will be lost because you cannot use it for science as well. So we try to explore other possibilities, and one of them could be to use or to benefit from the vortex chronograph. So the vortex chronograph is basically focal plane phase mask, which is transparent, and that will let any on-axis light be diffracted outside of the pupil area, where then a Leo stop can remove this light, so it's suppressed in the focal plane. Of course, if you have, even with a perfect vortex chronograph, if you have phase aberrations, light will of course leak, which is not necessarily a problem for focal plane reference sensing. So the most common vortex chronograph is the vector vortex chronograph. And what is particular with this implementation is that there are conjugated phase ramps applied to each circular polarization states, which means that in the focal plane, you would get a different signature for each polarization. So one idea would be maybe to split these polarizations and try to use the two resulting in focus PSF. There is also another flavor of vortex coronagraph, which is a scalar vortex coronagraph. And in this case, you have the same phase ramps applied to each polarization. And so here we wonder, maybe we can use just the in-focus PSF to do focal point of sensing. And to illustrate a little bit why it could be interesting, I use the same example as before with the two phase maps by just switching the sign for the event modes. As I said before, if you use a classical phase diversity with an additional defocus, we would get a different signature, which could maybe help leave the sign ambiguity. But here, what we propose is to either split the polarization states and get two in focus PSF. And in this case, you can see that we won't have any ambiguity because we won't have the same PSF for each polarization state. In fact, the signature is even switch between each polarization states. And so this is using a vector vortex coronagraph with splitting the polarization. But what you can also do is use a scalar vortex coronagraph. And in this case, you will just use the in-focus PSF without splitting any polarization as an input. Because the signature is different for the two phase maps. So just before I show some results, as I talked about in the first slide, we use a deep learning approach. So, I mean, already some people talked about this, and also Gilles Orban presented a bit convolutional networks. Here, I just wanted quickly to talk about a new architecture we're using, which is called EfficientNet. It's a bit more recent. It's from a paper from 2019. And it's quite interesting because it has been shown to perform quite well on, especially on ImageNet data, while having less parameters compared to, for example, ResNet 50. And their method is a bit different from the others because you use some kind of compound scaling method where it will scale the depth, the width, and the resolution of the architecture with a common parameter. I won't go into details anyway. I don't have time for this. I will just quickly talk about what we do to train our model. So in our case, we use simulated data. So we generate labeled simulated data with a known phase, a ground truth. So we use the input PSF as an input. Then our neural network will predict a phase map. We will compare it to the ground truth. We will compute a loss from this. And then this loss can be back propagated for the neural network to update the weights using gradient descent. And so through the epochs, you will improve your accuracy or decrease your loss. And we'll also use some validation loss, of course, to ensure that we generalize well enough to unseen data as well. So after training these models, we can analyze the results. And here, what I would like to do is just to show some results regarding the root mean square wavefront aberration for each Zernicke mode. So in black, you have the input level of aberration. And in light blue, what you have is what we get using just one in-focus PSF after the vector vortex coronagraph without splitting the polarization yet. And you can see that for the even modes, which means for the green areas, you won't get any correction, while for the odd mode, you will get some correction, which highlights the sign ambiguity problem. And if you use some phase diversity with a defocus PSF, like in darker blue, you will get a better performance, whatever the mode. But if we use the method we talked about by splitting the polarization states, we will get a similar performance. And if we use the scalar vortex chronograph approach with just one in-focus PSF, we still leave the sign ambiguity, even though the performance is worse. And it's mainly due to the fact that we have just one input instead of two to the neural network. We can also analyze a little bit the result, compare the root mean square wavefront aberration over the whole phase. So here, each point corresponds to one model trained at different signal-to-noise ratio. In our case, we just consider photon noise. And so what you can see is that in the other case, we of course get a stronger improvement using phase diversity. And if we use the split polarization approach with the vector vortex chronograph, we get similar result. And if we use the scalar vortex chronograph, a bit worse, like before. What we can observe is that if we compare to some theoretical limits that was set, we can see that for higher signal-to-noise ratio, we get far away from this limit. And this can be resolved mostly by using more training data. Here I was using 100,000 samples, but we could use more, use deeper architecture or more complex ones, or even some regularization techniques can be quite useful in some cases. So this was a bit about what we can get using simulations based on this approach, using the vortex coronagraph. But I also want to talk quickly about some other work we have been doing in parallel, which is using some experimental data, and in particular with the SCExAO instruments. So the SCExAO team provided us with some labeled data sets, so the PSF, but also the phase, which is applied to the DM, which is not necessarily the real phase in this case. And first, it was important to check that our simulation, are they close enough to the experimental data, which is quite the case, even though, as Sebastian talked about, there can be some limitation, especially for the out-of-focus PSFs. But what I just want to focus a little bit is to know whether we can benefit from our simulations to improve the performance of our model. So what I did is to first simply take different size of training in-lab samples and to check the root mean square Wavefront error using just in-lab data. So in-lab data for training and for evaluation as well. So if you don't have a lot of data, of course, you don't correct anything. But if you are far more, you improve the results. It is totally intuitive. And also the idea is to compare using simulated data. So for example, here what I do is that I train a model using a very large size of simulated data, and I evaluate on the experimental data I get. And you have some correction, but not that much. And the idea would be to combine the two, which is pre-train our model using the red one, and then fine-tune the model at the second step using the in-lab data. In this case, we have a very strong improvement, especially if we don't have a lot of experimental data. So it was a few experiments.
One more minute, Maxime, thank you.
Sure, I'm almost done. So it was just some illustration to show that we can benefit from a simulation and use some kind of transfer learning approach by doing a two-step, if you want, training. So to conclude, I just presented here some method based on focal plane of sensing using deep learning. I talked about some application of the vortex coronagraph. So it could be an alternative approach to leave the sign ambiguity and perform focal plane of sensing. I don't think I gave some motivation for this. And one of them is that if you use a defocus PSF, you will reduce your sign duty cycle because you will use some images just for Wavefront sensing and not for science. And so this could prove to be a good alternative using a vortex coronagraph, which is always quite used on telescope, especially the vector implementations. And also I just presented some results using experimental data. And the fact that with transfer learning, we can have some gain using simulated data as well. So thank you very much. And if you have any question, don't hesitate.
Wonderful, Maxime. Thank you very much for your presentation. We already have one question from Sebastian Haffer. How does the reconstruction compare to low order wavefront sensor, where the wavefront sensor is done with the light rejected by the Lyot stop? This is in the QA box. Yeah.
So I'm not quite sure to understand. So can you repeat?
Sure. How does the reconstruction compare to low order wavefront sensor, where the wavefront sensor is done with the light rejected by the Lyot stop?
So maybe we can discuss on this on Discord. I'm not totally sure to see the points. And
sure, maybe Sebastian, we can, if you like, you can also address the question in the Discord channel. Actually, there's another question already in the Discord channel. You can continue there. So thanks again for your presentation. We will continue then with the program.
Okay.
Thanks. Now we have Guyon An. Welcome, Guyon. You will present about a laboratory demonstration of machine learning-based focal plane wavefront sensing on Subaru. Guyon, maybe you can start sharing your slides if you're there.
Okay, can you hear me?
Yes, we can hear you very well.
Okay, I share my screen. So now you can
We
show.
can see. So
Yeah. So I will start.
Okay, we cannot see yet your
Yeah.
slide.
Okay.
One more
Sure.
minute. Now we can see it. All right. So remember, you have just 12 minutes. I will give you I will remind you in the last one minute. Okay.
Okay. Thank you.
You can start.
Yeah. Let's start. Hello, everyone. I'm Guyon, who is currently working at Subaru Telescope as a postdoc of the SCExAO team. So first of all, thank you for organizing this nice conference and giving me a chance to present my work. So today I'm going to talk about machine learning based focal plane wavefront sensing and show the lab demonstration on the SCExAO bench. Before getting to the point, I would like to mention the motivation of this work. So using the EFC, I made the high contrast zone, also known as the dark hole, in the focal plane of infrared camera with classical Leo coronagraph. And this dark hole has about 10 to minus 7 contrast, which is the deepest contrast ever obtained on the SCExAO bench. So also I implemented the linear dark field control to maintain the contrast of the dark hole. However, the LDFC has a very small linear range, so I was trying to find a good way to overcome this limitation of the LDFC. Meanwhile, I found the Gio's presentation about focal plane wavefront sensing with machine learning. So from this talk, I got inspiration and I started this work. So my goal is to maintain the contrast of the dark hole of IR image using the visible camera focal plane images with machine learning based focal plane wavefront sensing method. So the basic concept of this method is very similar to the phase diversity algorithm. So the phase diversity algorithm is working very well, but however, it needs accurate numerical model and many iterations to retrieve the wavefront. So to overcome these disadvantages, I combine the machine learning with phase diversity. So as you can see here, you only need 2 focal plane images as an input, and then you can estimate the wavefront without numerical model or iterations using the machine learning method. So, but for that, we need 2 pre-processes. One is the dataset generations for training, and 2 is the training the model using the neural networks. So I'm going to show the generation of the data set first. These 2 boxes in the center show the schematic diagram of the SCExAO bench. So the top one is the visible and the bottom one is the infrared bench. But I only highlight the optics that I used. So to generate the data set for training, I used the internal source and DM and 2 visible cameras. So I introduced the DM, I introduced the random phase map on the DM and recorded the focal plane images from the visible cameras. So I made 3 data sets with different wavefront error regimes for comparison. So each data set consists of 10,000 sets of the wavefront map focused and defocused images. For training, I used the ResNet 50 and UNet neural network, which have been already verified in GIS research. And the output of the ResNet 50 is the vector of the journey key coefficient, and the UNet output the wavefront map directly. And the loss function is like this. So I applied literally same method as GIS methods. So after the training, I implemented this on the SCExAO bench. So from now, I'm going to show the experimental results. So the left video shows the lab demonstration. Before started video, this big GUI shows the focused and defocused focal plane image of visible cameras. And this small GUI with Bruce Lee shows the DM channels. So we have 12 DM channels so that we can send the command separately. So in the actual implementation, I introduced a random DM map, random wavefront map on the DM channel 4 here, and I took the wavefront, images from visible cameras, and then reconstruct wavefront using two images and train the model. Lastly, I put the reconstruct wavefront on the DM channel 5 here. So after multiplying -1 to compensate for the wavefront map that I introduced on the DM channel 4. So let me start the video. So as you can see here, the correction is working well, and the reconstructed wavefront has a very similar shape to the introduced map with opposite amplitude. Also, the focus PSF after the correction is very close to the diffraction limit. Also, the right video is the summary of the left video. So as you can see, the residual errors are very small, and the closed loop PSFs are very close to diffraction limit and very stable compared to the open loop PSFs. Also, I compared this method with classical phase diversity. So I cited Gonzalez's paper to implement the classical phase diversity algorithm. So the upper figures show the result from the classical phase diversity. As I mentioned earlier, the classical phase diversity algorithm needs more than 30 iterations to find the solution. But machine learning based method doesn't need any iterations, also show better correction performance. So for more analysis, I also compared all results from the data set that I made. So this one is the data set number 1 and number 2 and data set number 3. So in the right figure, the solid black line that represents the mean RMS value of the input, and the red, blue, green plus mark represents the residual RMS of classical phase diversity, UNet, and ResNet 50 respectively. So as you can see, the classical phase diversity algorithm only shows a reasonable performance with small wavefront error regime like this. But open diverges only show the open diverges with a large wavefront error regime. So in contrast, UNet and ResNet show better correction performance and more stable performance, even with a large wavefront error regime. So UNet offers slightly better performance than ResNet 50. So I decided to use UNet neural network for next experiment. So for the next experiment, I implemented the machine learning based method with visible images to maintain the contrast of the dark hole in the IR image. So like the previous test, I generate the data set for training using the DM map and 2 visible cameras. But here I used eigenmodes to generate the random wavefront map instead of Jernicke mode, because it's easier to generate the speckles in the dark hole. So after that, I did same training using the new UNet neural network, and the right video shows the lab demo of the actual implementation. The top GUI GUI shows the DM maps, DM channels, and the bottom GUI with Chuck Norris shows the images from IR camera. So before this test, I docked the dark hole using EFC, and this DM map is the result of the EFC. So let's play the video. Yeah. So like the previous video, I introduced the random wavefront map on the DM channel 4 and to create the speckles in the dark hole, and took two visible images, which are not showing here. Using the trained model and those two visible images, I reconstruct the wavefront map and put this wavefront map on the DM channel 5. So to remove the speckles. So as you can see here, using this method, I could successfully remove speckles in the dark hole, I could successfully remove speckles in the dark hole of the IR image. So this is the last slide of my talk. So from these results, I confirm the feasibility of the machine learning based focal plane wavefront sensing method on the SCExAO bench. Also, I show that this method doesn't need iterations and it is flexible and robust regardless of changing the wavefront error legend. I also compared this method with classical phase diversity and confirmed that this performs better than classical phase diversity. So even with large wavefront error legend. In terms of future works, I need to do more analysis with different noise level and data set size, etc., for better understanding. I also will optimize and improve the speed of this algorithm for real-time focal plane reference sensing, because this method, as I mentioned earlier, this method doesn't need iterations or modulations to measure the wavefront in the focal plane. So we expect that it can be used with a 100% duty cycle in scientific observation. So for that, I will also do on sky test using this method. So that's all from me today. Thank you for your attention. So I'm happy to take questions.
Thank you very much for your presentation, very much on time. So we have a couple of minutes for questions. If somebody wants to ask Guyon, can do it in the Q&A box. Actually, I was just wondering, maybe I missed it from your presentation. What's the currently, what is the, how fast you can run this algorithm? So how much you have to improve it to go to on sky test or to go to real time?
So for on sky test, I need the speed of more than kilohertz, but now for only the reconstruction process, it takes the speed of the reconstruction is about 100 hertz, so it's not too very slow. But we are planning to upgrade the RTC computer, so I hope we hope that we can improve the speed of the algorithm. So do you expect that this is just a matter of hardware improvement, or? Yes. And I need to look into the algorithm to improve the speed of the algorithm. Yeah, sure. Also as well. All right, wonderful. Thank you very much again for your presentation. If there are any questions, you can use the Discord channel. So, all right. Yeah, thank you. Thank you. We reach now the last talk of this evening. So we welcome Olivier Guyon. I think, Olivier, are you there? Would you like to? Yes. Wonderful. Welcome again. This is an invited talk from Olivier about understanding and realizing wavefront sensing fundamental limits. So, Olivier, you like to start sharing your presentation?
Great, thank you.
We're not yet in, now we are in full screen. All right. Okay,
great. And you can hear me fine?
Yeah, very well.
Yes, first, thank you for inviting me and thank you for the organizing committee for this really great opportunity to get together and talk about our favorite topic. So I'm gonna sort of try to take a step back away from sort of a lot of the practical challenges and look a bit at the fundamentals of wavefront sensing, and revisit some old questions that I think myself and much of the community has been wondering. So hopefully we'll, a lot of my content is not going to have very specific conclusions, but hopefully will generate good discussion. I'll start with the wavefront sensor photon noise limit theorem. And it's in this red box, and what it states is that if you have n photon available and you have no other information, the limit, the photon noise limit, is such that you should be able to measure your wavefront with an error that's square root of 1/square root of n in units of radian RMS per mode that you're trying to derive. So that's essentially everything I'm going to say is derived from that. The easiest way to visualize it and check it actually is with a simple 2-aperture beam, and you're trying to measure one mode, which is the differential phase. So you're going to build fringes either in a focal plane or with a Michelson interferometer, measure the intensities, figure out what the photon noise is on these intensities, back propagate to the phase, and you're going to find that theorem holds. What's amazing about this is that if you put some numbers behind it, if you have 1 million photon, which is not unusual on reasonably bright stars, per wavefront sensor frame, at 0.5 micron, we should be able to get 80 picometer of wavefront error per mode that we measure. We're almost never approaching this, and so the question is how do we get closer, and why is it that much of what we do is not operating at this limit? So there's a few constraints, requirements for this to even have a chance of happening. The fringes need to be sharp. So in this 2-aperture example, basically, if the fringes are moving by more than a radian, if the phase is moving by more than a radian during the measurement period, the fringes will blur out and you will lose sensitivity. So that's a temporal coherence requirement. And the other requirement is spatial coherence. You need to have spatial coherence between the 2-aperture. And it matters a lot because that usually does not hold when we use laser guide stars, which are extended on sky. We can't just make pieces of the aperture interfere and hope to have fringes. An important note that will come back later is you don't need the wavefront error to be less than a radian. You just need to know it to less than a radian, either from the data itself or from auxiliary data. What that means is you can, in this example, for example, the fringes can be anywhere. If you don't know anything, and if you don't, you will have a one-wave ambiguity. But if you know your wavefront within a radian, that ambiguity disappears, and this will come back. So anyway, that's everything I'm going to say is derived from this. So we can look at simple example. Here's the example for tip tilt. The fundamental theorem tells us that if we estimate tip or tilt, we should get a standard deviation of 1/pi divided by the square root of number of photon of lambda over d in error. And this holds. This is exactly what you find when you do an optimus match filter on a PSF, diffraction limited PSF. You find that you get exactly that limit, and if you make the PSF broadband, you sort of deviate a little bit from that limit. So that's going to be a recurring theme, but not too bad. This actually illustrates a lot of the concept. You don't need to know where the PSF is before you take your image to get that precision. And the reason it works so well is that if you look at where you get most of the signal, which is the wings of the PSF, these pixels are actually coherent interference from the whole pupil, pupil plane. And that's why we get this sensitivity. Let's look at the Shah-Kartman. The Shah-Kartman divides the pupil into sub-apertures. So the first thing it prevents is a coherent mixing between lights that are between different sub-aperture. And that's why it has poor sensitivity to lower modes. And it gets worse as you try to put more sub-apertures. So again, there's a theme here. We're looking at a wavefront sensor as essentially an interferometer and looking at what interferences are made. And so we can look at various wavefront sensor and figure out what is their sensitivity. This is a figure from the paper I published in 2005. So this is an old problem that we're constantly revisiting. But, how different wavefront sensor map in this sensitivity. So what the two axes are angular separation, which is the equivalent of spatial frequency going from low spatial frequency like tip tilt on the left to high order modes on the right. And the sensitivity is on the vertical axis. Good sensitivity is in the lower part of the graph. 1 is the ideal, and bad sensitivity, poor sensitivity is in the upper part. And you see two families of sensor. There are the ones that maintain the horizontal lines, the ones that maintain very good sensitivity at all spatial frequencies. And then there are the ones which unfortunately are the most popular ones that have less and less efficiency basically at low spatial frequencies. And you can go in the lab and measure this. So we did it actually for the SCExAO pyramid wavefront sensor. You know, it's a pyramid wavefront sensor. So if we turn off the modulation in the lab, we find a very good efficiency. So again, you know, it may seem like 10% efficiency is bad. You have to keep in mind that if we plotted the Shah-Kartman on this graph, the efficiency would be 2,000 times lower than that. So we're actually, you know, this is demonstration. This is why we love pyramid wavefront sensors. They're very sensitive. And this, you can sort of break the wavefront sensor into families, the seeing limited ones and the diffraction limited ones. The seeing limited ones take advantage, don't take advantage of the coherence of the full aperture, like a Shah-Kartman. And the diffraction limited one, like a non-modulated pyramid, takes advantage of the diffraction pupil, the diffraction limit of the full aperture. And so this is the difference in sensitivity between having a D square sensitivity where increasing the aperture just adds more photon, or a D to the fourth, where increasing the aperture gives you more photon, but also you get an additional boost from smaller lambda over D. And so this makes a very big difference when we talk about large telescopes, and especially in what I work, which is extreme AO. So for tip tilt, for example, the difference between the Shah-Kartman wavefront sensor and this optimal limit is a factor of 40,000 in sensitivity, which corresponds to 11.5 magnitude. So this is not a small effect, right? We should really think hard about how to get as much as possible as this gain. And the gain is the largest on the lowest order modes. So taking this fundamental limit of wavefront sensor sensitivity, we can look at what's the optimal wavelength at which we should do wavefront sensing. And here the goal is to get the smallest residual in optical path length difference. And so there's a play between how many photons does the source give us at each wavelength, but also moving to shorter wavelengths gives us a better optical gain. So we get more leverage out of each photon because the error in the fundamental limit is in radian. So it's in phase. And so as we reduce the wavelength, that phase becomes a smaller number of nanometer in OPT. And so this is a table that lists this. This is a spectral type of star. So if we take a sort of a sun-like star or even a K-type star, we find that the optimal wavelength sensing band is B band. So this may be surprising to most of us because it's very messy to try to do wavefront sensing in the blue. But if we manage to, this would be where we would get the best, use the best sensitivity. And so, if you have a G-type star, for example, you might think, well, I'm going to do my wavefront sensing in H band because the wavefront's going to be really flat, so I'm going to be efficient. But if you do that, you're from the start, from the fundamental limit, you're taking a 33.7 times hit in sensitivity. If you manage to actually do the wavefront sensor in the blue, you'd be 33.7 times more sensitive. But it's hard, and it's hard because of a fundamental coherence challenge. When we look at this photon noise limit, we saw that one requirement is you need a good wavefront sensor, a good wavefront knowledge to actually get that sensitivity. And if you do your wavefront sensing in the blue, very often you don't have that. You struggle to basically get this. I want to stress the word knowledge. You don't actually need a wavefront that's diffraction limited to get that sensitivity, but you need to know what it is. And falling back to the very simple case of centering of a PSF, it's you don't actually need diffraction limit. A cloud of speckle would work as long as you can compute that cloud of speckle, and the only thing you're trying to do is figure out where it is because the speckles are diffraction limited. So this drives us to try to explore this question: why are wavefront sensors failing to maintain good sensitivity when the aberration level is more than a radian RMS? If we solve this question, we can actually move our wavefront sensing in a regime of full coherent sensitivity, and also have the flexibility to go at the optimal wavelength. So this is a really essential question to answer. And there are two reasons why our wavefront sensor schemes fail to work when we at high sensitivity, when we have large level of aberration. The first one is a loss of optical sensitivity. And there's really nothing to do about this, except throwing away the wavefront sensor and building another one that's different. But there is another loss, which is a loss of linearity. Sometimes you still have optical sensitivity, but the signal is not linear. And then you need a better wavefront sensor reconstruction algorithm. That's what we should be focusing on moving forward in the future. And a lot of the talks that we just heard about are pushing exactly in that direction. Let me illustrate this. What is an example of a wavefront sensor that does very well when the wavefront is flat, but for which the optical sensitivity basically drops as the wavefront is no longer flat? It's the pyramid wavefront sensor. So that's an example. If the PSF is centered and high strail on the apex, the tip of the pyramid, we get very good sensitivity for all of the modes. But as wavefront errors increases, we no longer have a concentrated PSF on the tip, and we lose optical sensitivity. The simplest example is, what if there's a tip tilt excursion? Most of the light moves into one of the pupil. If you put a little bit of astigmatism here, it will not change the intensity you measure. There is no way to recover from that. You can have all the machine learning algorithm you at your disposition and try them. The problem is there is no signal. There's nothing. You know, that's an example where perturbation in the wavefront gives you absolutely no signal in the camera, in the detector. So that's what I think the next frontier is, to try to avoid this situation. So here is another example so the other case, a loss of linearity. It's the good old curvature wavefront sensor, which we sort of abandoned, but I'm gonna make the case that maybe we shouldn't have. And you basically look at wavefront out of the pupil plane, and you see intensity modulations that are a function of the curvature of the wavefront. So here is a simulation where you do a cut in the z-axis. As you move away from the pupil, you see this modulation in intensity that essentially encode the wavefront itself, especially the curvature if you do a linear reconstruction. And this is the signal itself, the difference between a plus and a minus altitude, where you can see the positive and negative signals encoding the curvature. It turns out that the signal is still there if you have a large wavefront aberration, but it's not linear. It's very difficult to extract. So here is here's an image that shows it. This is a defocused pupil image. These tiny speckles are actually diffraction limited. If you actually knew how to reconstruct these speckles from higher order modes, you could, for example, compute the tip tilt with the lambda over d diffraction limited sensitivity. But the problem is everything's coupled together. If you can't reconstruct the higher order modes, you can't reconstruct the lower order modes, and vice versa. So everything, it's a challenging reconstruction, but there's a rich history of people doing phase diversity. So we can actually explore this. And this is an important plot that I'm going to spend 2 minutes explaining. This is different wavefront sensors sensitivity. So sensitivity is on the vertical axis, and spatial frequencies in the horizontal axis. And here I'm plotting the sensitivity of various wavefront sensors schemes as a function of spatial frequency. And what you see, so this first plot, top left, is for no wavefront error. What we can see is these very two clear families: the seeing limited wavefront sensors, which have poor sensitivity at low spatial frequency, and the diffraction limited wavefront sensor, which include here the pyramid. This is a non-modulated pyramid, and the curvature sensors, the non-linear curvature wavefront sensor, sort of phase diversity. By the way, the curvature linear wavefront sensor is not particularly good. So the way we used to do curvature wavefront sensor is not, it's like a Shakhartman essentially. It's not operating in a diffraction limited regime. So anyway, that we knew already. There's no big surprise. The surprise comes out when we increase the wavefront error. So this is 4 radian RMS on the wavefront. And now we can see the pyramid peels off. it no longer provides the optimal sensitivity, but the phase diversity or nonlinear curvature actually stays near the optimal sensitivity. The other thing that happens is it used to be that we had two pyramids here. There was a red line and a purple line that were on top of each other. One is a linear reconstruction and one is a nonlinear reconstruction. And you can see that here they start to peel off. The linear reconstruction does very poorly. The nonlinear one does a little bit better. And I cheated here. I don't have a reconstructor for the nonlinear pyramid. I explored the Kramer-Rao bound, which is a mathematical bound. It's a perturbation analysis that no algorithm can cross. It's basically propagating photon noise into the solution. And so you can see as you increase the level of wavefront error, you actually get the situation where all of those wavefront tensors get worse. Even the optimally nonlinear pyramid reconstruction is not particularly very good, although it tends to level off at some level. But this phase diversity algorithm still maintains optimal sensitivity. So that, I'm not saying we should build this particular wavefront sensor, because actually there are significant challenges in realizing this at high speed. But it really points us to an interesting direction where there are options that allow for all of these good things to happen. So let's try to do wavefront reconstruction. This is the input data on the left. So here I put 4 planes because 2 planes don't give us quite enough information. So it's a 4-plane phase diversity. With only 20,000 photons. The input wavefront error is 609 nanometer, and the reconstruction gives, which is shown on the right. So this is input wavefront on panel E, residual from the reconstruction on panel G. We reconstruct the wavefront with an error of 34 nanometer, which is actually consistent with the photon noise limit theorem for about 2,000 modes. So it's very encouraging. So if you wrap that in closed loop simulation, this is what we get. This is the loop off. And now we have 5 different cases, 4 Charcot-Manns with different subaperture size and the nonlinear curvature, so phase diversity running in closed loop. And you can see the significant gain in performance. So the Charcot-Mann optimal subaperture size is somewhere between D/18 and D/36. But it peaks at less than 20% STREL in the red visible, and the phase diversity goes to almost 60% STREL. And this is on a magnitude 13 star on an 8-meter telescope. So it's actually pretty good. It works well on highly segmented aperture because there's good mixing between the segments. So checks off the box of low wind effect and so on. But here's the problem. At some point, there is, when I showed this theorem, there was a requirement of temporal coherence. The wavefront must be stable to less than a radian RMS during the measurement period. At some point, we don't have enough light to maintain this. And we basically fall off a cliff. So this is guide star brightness. Bright is on the right, faint is on the left. You can see as the star gets fainter, the RMS residual error doesn't just simply gradually increase, it falls off a cliff. We transition from the Singh limited regime to Singh limited regime on the left to diffraction limited regime on the right. The name of the game, I think, is going to be to push that limit the furthest possible to the left to fainter stars. One thing we can do to do that, which is shown in this plot, is run the wavefront sensor at longer wavelength to maintain coherence at longer wavelength. So it starts to paint a picture where we'd like to have wavefront sensing at longer wavelengths to grab this coherence. But once we grab it, also have shorter wavelength wavefront sensor to boost the sensitivity. And one thing, and we heard about this earlier yesterday, one thing that's going to help a lot is also predictive control. So this is on-sky results from predictive control, which really shows that we can use measurements that are 10 to 20 milliseconds old with very good information content. So the coherence time essentially is increased, leading to a boost in sensitivity. So wavefront prediction should actually help us move this limit further to the fainter stars. I'm going to finish by mentioning that I think probably the most promising direction is interferometric wavefront sensing. We heard about it from Sébastien Vievard and Vincent Deo and others. This is an example of on-sky interferometric wavefront sensor measurement in the visible. And you can see fringes that encode both the wavefront and actual information about the source, dispersed as a function of wavelength. And there's several ways to realize interferometric wavefront sensing. This is another way. This is a glint module on SCExAO, which is actually an interferometric nuller. It gives you null output, which are science for us, at the same time as it gives you wavefront sensor measurements as a function of wavelength again. So these things are very powerful, and you start to see this theme where you can actually mix them with the science measurement. So you don't just measure the wavefront, you also measure something about your object. And I want to finish with this slide before my conclusion slide, which is showing something a little bit more fundamental about why interferometric wavefront sensing is fundamentally superior. Much of the problems we run into is this sort of catastrophic cascade of failures, where if you drop part of the coherence on a mode, the other modes crash. So you get in the situation where the wavefront sensor in low flux is not stable. So here is an example of a simple 4-aperture telescope. So there's a pupil. So you have 4 apertures. There's only 3 wavefront modes you can measure. A minus B, A minus C, and C minus D. If you take a focal plane image after that, you will see 4 baselines, 4 peaks in the UV plane. 2 of them are summed. They're ambiguous. They're AB plus CD because they're the same baseline, and AC plus BD because they're also the same baseline. But you're okay. You measure 4 complex visibility. You have 3 wavefront modes you're trying to get. So you're going to get a fully constrained wavefront. Plus, you get a bonus. You get 1 phase closure, which gives you an information about your object. Now, imagine that you break coherence between the AB group and the BC group and the CD group. For example, if the star is elongated or double star, or it's oscillating rapidly in the vertical direction, you lose fringe visibility between A and C, and B and D, and B and C, and A and D. So you can only measure 2 wavefront modes, A minus B and C minus D. This is shown here. The problem is you only measure one thing in the complex amplitude, which is the sum of the AB visibility, complex visibility, and CD complex visibility. You have no way to separate the two. So you will make one measurement for 2 modes. You're basically dead in the water. You can't reconstruct anything about what you're looking at. If you remap this, which an interferometer lets you do, you basically rearrange this in an interferometer so that you have unique fringe output. Then you recover actually all of what you were supposed to measure, A minus B and C minus D. And the reason it's important is because that's the key to making wavefront sensor more robust, is to avoid this catastrophic sort of breakdown because one mode drops, everything else drops. And so my conclusion slide is here. I think this cartoon really illustrates the challenge in front of us to have high sensitivity wavefront sensing. We need good wavefront sensor, good wavefront knowledge. But to get good wavefront knowledge, we also need high sensitivity wavefront sensing. It's the sort of the rich get richer and the poor get poorer kind of situation. We're stuck in this loop. If we're on the right side of the loop, everything's good. We can actually get this amazing sensitivity. But if we're on the wrong side of the loop, we fall immediately on the very poor sensitivity regime, the seeing limited sensitivity. And the difference between these 2 regimes is extremely large for large telescopes. I think that's it. I mean, I talked about everything that's listed below. Hopefully there's time for questions.
Thank you, Olivier. Thank you very much for your presentation. And yes, of course, we have some time, a few minutes for questions or any comments from the audience. You can use the Q&A box, of course. Yes, I just kept thinking about something. You said, you mentioned, I think, that going to longer wavelengths, right, is one of the one of the paths that one could follow. So that means that there's just a technological challenge, right, to develop sensors working fast and large, also at longer wavelengths, no?
To some degree, yes. I think that technology challenge is being addressed. We have detectors now that are available to us that are essentially approaching the photon noise limit in the near infrared at high speed. You know, the avalanche MCT detectors and MKIT detectors are basically there or almost there. So yes, so basically the reason we want to go to the infrared is to grab this coherence regime. But as soon as we grab it, we should try to extend it to bootstrap our way to shorter wavelength, where we're going to get, you know, I showed this 33 time gain in sensitivity. So there's basically, we're stuck in this painful trade-off now. We either go in the infrared, where we have high coherence, but poor optical gain, or we try to work in a visible, where we don't have the wavefront quality we need to actually take advantage of the high optical gain that the visible photons should give us.
All right, thank you. There's a question from Vincent on the Q&A box. He says, I have a question on your theorem. I thought that actually the Kramer-Rao formula gives a variance of the phase equal to 1/4 number of photons, which is slightly different from 1 number of photons.
So I'm not sure I fully understand the question. Let me first explain what I did here. What I did is I basically, for each realization of a wavefront, I computed a large number of photon noise realizations, and I compared that with the local derivative of the image that the wavefront sensor gives against as a function of wavefront perturbations. So I basically converted a sigma, a standard deviation that's due to photon noise, into wavefront sensor space using local derivative, the local derivative of the wavefront sensor image relative to the wavefront phase. And so that's a limit you can never cross, because you're always going to have photon noise. And so it's a limit that's completely independent from the algorithm. It's, you know, no algorithm can cross that limit. I hope my answer is clear. I'm not sure
I know Vincent or Vincent, if that's clear for you, satisfy your question. Hopefully, yes. All right. I think we're already on time. It was a very intense day. So I think we thank you again. Thank you, Olivier, for your presentation. And we thank all of the speakers of today. So we're closing now the session. We're closing the day of this workshop. And so I thank all of you. And I think we are meeting again tomorrow at 10 a.m. local time in Chile. So thank you very much to all of you, and see you tomorrow. Goodbye.